Hey there, folks. Happy Tuesday. Today's problem involves the conservation of momentum again, and we're applying it to an extremely radioactive element, polonium. We're told that a nucleus of this substance will decay radioactively by emitting an alpha particle, and we're given that particle's mass and kinetic energy. It's up to us to figure out how fast this leftover nucleus recoils in the opposite direction. We know that since the original polonium nucleus was stationary before the decay, the initial momentum has to be zero. And by the conservation of momentum, if the total is zero in the beginning, well, it has to be zero in the end, too. We'll call the direction that the alpha particle moves in the positive direction, so that the individual momenta of the alpha particle and the new nucleus are negatives of one another. And if you add them up, you'll get the final momentum of zero. This is a really nice setup because we can take the second term here and move it over to the right-hand side and equate these two. Let's plug in the definition of momentum next. What we want is the velocity variable here on the right. You can probably tell that we're going to divide both sides by the mass here in order to get this. But it's not quite clear what this mass represents. So allow me just a few moments to explain a couple things first. Let's start with nuclear notation. The 214 in our polonium nucleus is what's known as the mass number, and that represents the total amount of protons and neutrons in this element. Every proton and neutron has a mass, and in fact, their masses are nearly identical. This means we can get a pretty good approximation of this polonium nuclei's total mass if we took the individual mass of one of these subatomic particles and then multiplied it by 214. And that's exactly what we're going to do. Let's ignore the super tiny differences in mass between these and just use three significant figures. So 1.67. I'll label the mass of one of these individual subatomic particles lowercase n for nucleon, which is a particle physics term which means proton or neutron. Thus, the total mass of our 214 polonium nucleus can be expressed as 214N. What about an alpha particle? Well, that's an atomic nucleus as well. In fact, it's identical to the nucleus of a helium atom. If we use nuclear notation, it can be represented like this. The problem description gave us its mass already, so instead of approximating, we'll just use that number. Now, I've brought all this up because we'll need to use this information to figure out the mass of the resulting polonium nucleus once it loses 4 nucleons due to ejecting the alpha particle. The new mass number becomes 210, and now we have an isotope of polonium that's one of the most hazardous radioactive materials in the world. A bit of an interesting tangent here. I remember a very famous story back in 2006 when an ex-Russian spy in London was poisoned by a very tiny amount of polonium-210 when it was slipped into his tea. It's extremely dangerous stuff. But anyway, let's get back to getting the mass of this new isotope so we can solve this problem. We'll take 214N and subtract the provided mass of the alpha particle. If we plug in the nucleon mass definition and put this all into a calculator, we'll get a result of about 3.50 times 10 to the minus 25 kilograms. With that known, let's go back to that momentum equation we had earlier. We're now aware that polonium-214 minus an alpha particle is polonium-210, so let's update this expression. If we divide both sides by the mass of this isotope, we get the velocity that we wanted, but we're missing the velocity on the left, which belongs to the alpha particle. Let's do a couple steps on the side to get that real quick. We were provided with the kinetic energy of the alpha particle, and that's equal to 1/2 mv squared. If we multiply that kinetic energy by 2, divide by the alpha particle's mass, and then take the square root, we can use this expression as a substitute for its velocity. And I'll plug that in down below. At this point, there's nothing left to simplify or exchange, so we're free to plug in our numbers and finish this up. My calculator gives the following answer, and hopefully yours does too. That's all for now. Thanks for watching.